Good morning everyone. So this is my next lecture, lecture number 17, based on bipolar junction transistor. So in the last lecture we have seen bipolar junction transistor, what are the different type of junction transistor, either it will be NPN or PNP type of transistor, and then we have seen about the different configuration of the bipolar junction transistor, that is common base or common collector or common emitter configuration. So in this lecture we are going to see what are the limits of operation for bipolar junction transistor. So many BJT transistor used as an amplifier, as we have seen that what are the applications of BJT. In the active region we can use as an amplifier, in the saturation region we can use as a switch, and so on. So many BJT transistor used as an amplifier, thus it is important to notice the limit of operation. So we have to notice what is the limit of operation. So at least 3 maximum values is mentioned in data sheet. So there are maximum power dissipation. So we have maximum power dissipation, which is written here, that is PC max or PD. Maximum collector emitter voltage, that is VCE max. Sometimes it is referred as VBR CEO, or we have seen in the last lecture that VCEO. So maximum, and next one is the maximum collector current, that is IC max. So these are 3 maximum values which is mentioned in the data sheet. That is, first one is the maximum power dissipation at the collector side. Then maximum collector emitter voltage, that is VCE max. Then next one is the maximum collector current, that is IC max. So there are few rules that need to be followed for BJT transistor, which we can, how BJT transistor can be used as an amplifier. So we have to follow those rules also to make it to use to having a use as an amplifier. So first is the transistor need to be operate in the active region. So as we have discussed in the previous lectures that there are some differences between the active region, the saturation region and the cutoff region. So we have seen that after some time when you increase the voltage, the current will increases drastically, and that is the region which is called as your linear region or the active region. Below the linear region there is saturation region, and below VB or IB is equivalent to 0, less than is equivalent to 0, that the values are there where there is no current flowing, is your cutoff region. Whenever you increase the voltage and there is no current flowing in the circuit, that is known as cutoff region. So firstly, for using the transistor as an amplifier, the transistor need to be operated in an active region. Also the second point is obviously IC max, that is the collector current, which is maximum collector current, should be maximum than the collector normal collector current. Similarly, the power at the collector is maximum, which is having a value which is greater than PC normal collector power. So you can see from the graph there are some operating points which we have obviously in the last lecture we have seen about the operating points. So in this graph there is a graph between VCE max, which is basically VCE voltage in volts, and IC in milliampere. So the graph is between VC and IC. The maximum value of here we have noted, because there are some operating points we have noted. So this operating point, the first one, the second operating point, the third operating point, and the fourth operating point. So at this operating point we will get the value of the VCE max. Similarly at this operating point we have a value of PC max, which is equivalent to VCE minus IC. Obviously power is equivalent to voltage into current. So by getting the value of VCE value here, that is 10, and obviously IC value, that is 30, we have a power around 300 milliwatt for the PC max value. Similarly we have IC max value, which is around 60 microampere. So with this load line, or you can say this is the load line curve. This region is your cutoff region. Below the black line we see saturation region is there, and above the cutoff region there is active region. So at the active region we draw a load line, and in this line we have fixed the operating points. We have some operating points. So with this operating points we can get the value of VCE max, we can get the value of VCE max, we can get the value of PC max, and we have the value of IC max. So these 3 parameters we should know to make a transistor to use as an amplifier. So here VC max is at maximum and IC is at minimum. So IC max is equivalent to ICEO, and which is in the cutoff region. So IC is at maximum and VC is at minimum that is VCE max is equivalent to VCE saturation, which is equivalent to VCEO in the saturation region, and the transistor operates in the active region between saturation and cutoff, which we have seen in the graph. So next we have the graph is same, which is basically we are created a load line on the curve, on the characteristic curve between VCE and IC. So what is load? It is defined as a device across which the output is taken for a given circuit or for a given input. So load line, it is defined as a line which crosses on and off points of BJT. So there are some points in the BJT characteristic curve which are on points, and there are some points which are off points. So basically this load line or will cross these points, or these points are also known as quiescent points. So center of the characteristic is called as active region. So at the center we have the active region. Region near collector current is your saturation region, and region near the collector voltage is your cutoff region. So we have the region near the collector voltage is the saturation cutoff region. The region near the IC, that is the collector current, is your saturation region, and the center of the characteristic is basically your active region, which we can show here with the blue lines. So we have BJT equation. So in the last class we have discussed about different equations which will give you the value of the emitter current in the form of the base current and the collector current. So we have with this graph, the first picture is for PNP transistor, and for PNP transistor we have common base configuration. So current is flowing from the emitter to the base side, and similarly the current is flowing from the base to the collector side, that is IC. So here there are three currents mentioned in the graph, in the picture, that is IB, IC and IE. And overall, if you see the equation, that IE is the inward current and the IC and IB is the outward current. So that's why IE is equivalent to IB plus IC. First equation is this, we have to notice. Then we have a voltage between base and emitter, which is basically VEB or VBE you can write. And similarly the voltage between collector and the base, that is VCB, which is written here. So we have two voltages between VBE, one between VBE and other one is between VBC, and similarly we have a voltage between collector and emitter, so which is VEC. So whatever the situation is, if it is a common base configuration, then we have a voltage between emitter and collector and base. If we have a common collector configuration, then we have a voltage basically VEB and VEC. Similarly for the common base configuration. So in the second picture we have NPN transistor, and here also we have drawn the same thing, that is base, emitter and collector terminals, and the inward current is here IC and IB, and the outward current is here IE. The equations are same, that is I is equivalent to IB plus IE. So here the equation is same, that is I is equivalent to IB plus IC. Similarly, we have all the voltages sum. Either it will be VEB, VCB or VEC. All the voltage sum should be 0. So from here we can write VCE is equivalent to minus of VEC. We can write in the both ways. So as shown, the currents are positive quantities when the transistor is operated in forward active mode. So we have come to the conclusion that we have the current which are basically in positive quantity, and when we operate the transistor in the active region or in the forward bias region. So here we have different cases. The first case is case 1, where IE is equivalent to IC plus IB. So when you substitute the equation, that is you have IC is equivalent to beta IB into equation number 1, you will get IE, that is the emitter current, which is equivalent to beta plus 1 IB. Case 2 is for alpha and beta, for calculating alpha and beta. So alpha is basically your input transistor gain, that is IC upon IE. Similarly, beta is your collector or output gain, that is IC upon IB. So from here we have IE is equivalent to IC upon alpha or IB is equivalent to IC upon beta. And if you put the value equation number 2 to equation number 3 here, you will get a relationship between alpha and beta, which we have seen in the last class also. That is alpha is equivalent to beta upon beta plus 1, or beta is equivalent to alpha upon alpha plus 1. So while getting the value of alpha or beta, we can easily find out the other value. So if we know the beta, we can easily find out the value of the alpha. Similarly, if we know the alpha, we can easily find out the value of beta. So next we have Ebers-Moll's model. So this model is basically used to describe the current flowing in the BJT in both the direction, and BJT is basically a circuit having two diodes connected back to back. We already seen. So when we connect two PN junction, we will having a BJT or bipolar junction transistor. So this model analyzes the same circuit. So here we have back to back PN junction. From you can see from the picture that we have anode part here and then cathode part here. Similarly, anode part here and cathode part here. And we have connected with the terminal as shown in the picture, that is emitter and the base and the collector terminal. So the current is flowing from base towards the collector, and here the current is from the, through the emitter towards the collector, and similarly IC. So we have all the equations are same, that is IE is equivalent to IC plus IB, as we have known here that the inward current is equivalent to outward current. So the inward currents are IC and IB and the outward current is IE. So we have the equation IE is equivalent to IC plus IB. Similarly, in the second case, we have taken cathode, anode upward and cathode below. Similarly, cathode and anode. So this will form a basically NPN transistor. This is NPN transistor, and this will form your PNP transistor. The equations are same for the current, that is IE plus IB, means IE is equivalent to IB plus IC. Here IB and IC are the outward currents and IE is your inward current. Alpha F and alpha R is the forward gain and the reverse gain for the particular circuit, that is for the one PN junction, that is for collector and base junction. So that's it is shown here, and then for the second junction it is shown here in the next part. Similarly, we have the current alpha R and alpha F, that is the reverse current and the reverse current gain and the forward current gain for the PNP type of transistor. So what are the equations here? We have the equation in the form of IE is equivalent to IS e to the power VB upon VT minus 1, which is your diode equation, minus alpha R ICS e VBC upon VT minus 1. Similarly, we have the second equation for the IC. So here the terms are written here, that is IE is your emitter current, IC collector current, alpha R reverse current gain, alpha F is your forward current gain, VT is the thermal voltage. Similarly, IES is the emitter saturation current, ICS is the collector saturation current, and VBE is base to emitter voltage, then VBC is base to collector voltage. So these equations are basically from the diode equations we have written for I is equivalent to IB plus IC, or for IC is equivalent to IE minus IB. So next we have metal oxide semiconductor. So basically MOS and in the, if you see the MOS and the BJT, both are almost same. They have both the things have the same number of terminals, that is emitter base junction in the case of the BJT, and in the case of the MOSFET it is gate drain source. So MOS is metal oxide semiconductor structure in which metal is basically aluminium, and what is oxide here, it is silicon dioxide, and what is semiconductor here, it is silicon. So basically it is known as MOSCAP, which is metal oxide capacitor, which is a semiconductor capacitor used to replace physical capacitor in basic electronic circuits. So in basic electronic circuits, if you want to represent a physical capacitor, so you can represent that with a MOSCAP or metal oxide capacitor. So here we have a MOSCAP structure, which is p-type semiconductor is the base. The oxide, the silicon dioxide layer is upward on the semiconductor, and then there will be a metal layer. So we have a gate point here, the base is here, that is B, and your drain is in between the gate and the base. So we have the oxide layer in between the gate and the base. The thickness of the oxide layer is given by TOX. So this will represent your MOSCAP. It's a kind of a MOSFET semiconductor. So in structure of MOS capacitor is basically, the structure of MOS capacitor has source, gate and drain terminals. As I have told you that it has 3 terminals, source, gate and drain, where source is your, in the same way like in the BJT we have the source is emitter, the gate is your base and the drain is your collector. So if you see the analogy between both these BJT and the MOS structure, it is similar to them. So we have the source as emitter, the gate as a base, and the drain as a collector. So these terminals have the same function as that of BJT terminals, which I have written here. So oxide layer here acts as a dielectric between the gate and the source. So here MOS capacitor picture is shown where N plus depletion layer is there. We have a P type of substrate, and above the P type of substrate we have a gate layer, and then we have a insulated SiO2, that is silicon dioxide, and then we have a connection with the gate, and the drain is N plus, which is highly doped region. So this is highly doped N type of semiconductor. So for doping we have to add impurities into the normal N type, normal semiconductor. So if you want N type of or N plus highly doped semiconductor, we have to add pentavalent type of impurities. So in the below figure we have represented the same thing in a particular way, that is the silicon substrate here, then SiO2 layer is here, then polysilicon gate. So we have gate, then we have a source, that is, so the structure of the MOS capacitor is same. Here the silicon substrate, then silicon dioxide, then polysilicon gate. So we have this type of structure. The channel length is L, the drawn length is L here. So the depletion layer is in between the substrate and the gate, and we have the overall picture, that is the as same as the BJT transistors. So next we have flow of current in MOS capacitor. So here formation of charge takes place on the surface of the oxide layer as the voltage is applied across it, and flow of current is in a specific direction. So we have a particular MOS structure here, and we have P type of substrate. So this is P type of substrate here. We have applied a external voltage, external battery, and the gate terminal is here. So this is your SiO2. Okay. So the gate terminal is connected here. The substrate is of P type, and the N plus depletion layer is formed here. The field direction is from positive to negative side. So we have the external battery connected. So the whatever the SiO2 have the electrons in the layer will attracted towards the P type of region, and then there will be accumulation of electrons in the P type of region. So this will give you the flow of the current in the MOS capacitor. So next we have energy band diagram of MOS capacitor, as we have already discussed about the energy band diagram of PN junction. So we have PN junction like this. So the energy band diagram is like this, and we have EF, Fermi level is here. So we have EV, EC for the P side, and similarly we have for the N side ECN and EVN, and this is your depletion layer or the barrier. So this is for the PN junction. We have a built-in potential VBI, which is KT by E ln ND NA upon Ni square for the case of the PN junction. So similar in the same way we have for the MOS capacitor. The MOS capacitor exhibits a band diagram where the bending of band takes place according to the work function at the interface. So here also in the PN junction we have seen the work function, that is phi Fn, the Fermi level work function for the N side and the Fermi level work function for the P side. So according to the work function we have to set the barrier potential so that the number of electrons in the N side will cross or jump towards the P side. So and the holes will move towards here. So that's why the band bending will be shown in the case of the PN junction or the transistors. So in the same way we have a bending in the case of the MOS capacitor. So here there is a vacuum level and the Fermi level is in between, again the valence band and the conduction band. So we have the vacuum level, the work function here is Q into phi m because it is a metal here, and then we have Similar way, valence band in the semiconductor, because if you see the picture, that it has a metal, insulator and semiconductor. In between it is insulator. So metal has a higher work function, that is Q phi m. Then we have a Fermi level in between the metal and the semiconductors. We have EC, which is the conduction band state, and then valence band state. Then in between conduction and valence band, we have a Fermi level EF, which has a work function of Q into psi b. Then we have a energy band diagram, band gap between EC and EV, which is shown here EG. So here EG is your energy band gap. Q phi m is the work function for metal. Then we have Q phi psi b or Q psi b, which is the work function for the semiconductor. So work function for semiconductor. So we have different work function for metal and semiconductor and the energy band gap, and by this way we can see the band bending between the metal and the semiconductors. And in between, the as in the case of the PN junction, we have depletion layer or the barrier potential. We have a insulator here, and which has a work function of around Q into psi. So MOS capacitor exhibit a band diagram where the band bending takes place according to the work function at the interface. So the diagram of the capacitor gives the internal structure here. And MOS capacitor has three regions of operation basically. The first region is accumulation, then depletion, and then the last region is the inversion. So we have, as in the case of the BJT, we have three regions of operation: the saturation, active, and the cutoff region. Here the region of operations are different, which is accumulation, depletion, and inversion region. So structure and if we see the structure and principle of the MOS capacitor, in the first we have shown about the accumulation, and the second one is the depletion, and the third one is the inversion. So in the first we have the gate voltage is less than the forward biased voltage. Whatever the battery, external battery you are applying, that is more than the gate voltage. So we have same back contact here, P type of substrate, gate, semiconductor oxide layer, and obviously P type of substrate have number of holes, more than number of holes. So if we connect positive voltage here and negative voltage here, so positive is rippling by the number of holes here, and that all the holes will accumulate towards the P type, or the negative ions will accumulate towards the P type of substrate. So that's why we have to see here that forward biased voltage is much higher as compared to VG. That's why only in that case the accumulation will occur. The accumulation of the electron towards the P type of substrate will occur here. Similarly, in the depletion region, we have to deplete the number of electrons from the substrate. So we have to change the voltage. Here VG should be much greater than VFB, which is your forward biased voltage, and less than the threshold voltage. Similarly, in the inversion region, what will happen? In the inversion, what will happen? The gate have maximum number of holes, and the P type of substrate has maximum number of electrons. So here VG must be greater than VT. So these three type of region of operations are here for the MOS capacitor. The first one is the, again we can say that the first one is the accumulation, which is your accumulating number of electrons in the P type of substrate. The second is the depletion, so depleting of the number of electrons from the P type of substrate, and then last one is the inversion. So we have in the inversion, the number of electrons will be maximum in the P type of substrate as in the gate region. So these three structures will give you the overall picture of the MOS capacitor, how to use MOS capacitors in different applications. So the next one is the principle of operation of the MOS capacitor. So we already discussed about in accumulation, in this mode positive charge is developed in the semiconductor and negative charge in the metal. So we have maximum number of negative charge in the metal side and positive charge in the semiconductor side. In the depletion, in this mode negative charge is developed in semiconductor and positive charge is developed in the metal. So it is opposite to the accumulation process. Here the positive is accumulated in the metal and the negative charge is accumulated in the semiconductor. In the inversion, in this mode large negative charge is developed in the semiconductor and positive charge in, because we are taking P type of substrate as a semiconductor, so large negative charge is accumulated in the P type of substrate and positive charge in the metal. So it's a inverse process of the accumulation process. So we have three diagrams showing accumulation, depletion and inversion here. So we have P type of substrate here, as we have taken already the P type of substrate here. Then we have an oxide layer, which is SiO2, then negative charge. So more number of negative charges are accumulated in the P side and the semiconductor side, and the more number of positive charge in the metal side, then that will be called as accumulation. Similarly, more number of negative charge, less number of negative charge in the P side, and less number of positive charge in the N side, that will give you the process of the depletion. And in the third one, we have the inverse process, that is more number of negative charge in the P side substrate and the more number of positive charge in the N type of substrate. We have N type of metal, then we have the inversion process. So these three processes will give you the how to use these metal oxide capacitors as in a particular application. So this is NMOS capacitor. You can also draw for PMOS capacitor. So for PMOS capacitor, the substrate is of N type and the metal is of P type. Thank you so much. So in the next lecture, what we are going to see, we see how these metal oxide semiconductor capacitor can work in future in various applications, how these metal oxide semiconductors will be used, capacitors will be used in different industrial applications. Then we will look after into LEDs, that is light emitting diodes, which are the best example for semiconductor devices. Then we will see about lasers. So lasers and LEDs are basically the sources for the semiconductor devices, and these sources can be used in different applications. Either it will be an optical fiber or it will be in different digital circuits. We can use LEDs and lasers. Similarly, we will see the detector part also in the few lectures later on. So in the detector, we will see about pin and avalanche type of photodiodes, how these pin and avalanche photodiodes will work when the light will fall on that, and they will give you electrical current. So they will convert the light into electrical current. How there is the conversion and what is their efficiency. In terms of efficiency, we will compare the pin and avalanche photodiodes. So thank you so much. We will meet in the next lecture.